Have you scanned the QR code? Okay, let's start the class. I hope that you can hear me.
Yes, Professor, your voice is clear.
Okay, thank you. And also the screen is with you. So let's keep going talking about static tests. Last week we saw some key factors in two specific static tests, the ones that we call limit and ultimate load factor test. The difference between these two is simply because of the loading. We are starting with the limit load factor by statically exciting the structure, referring to the limit loads, and these limit loads can refer to whatever flight phase, from taxiing to cruise to bending to whatever. Okay, and the purpose of this test, such a test, is to verify the numerical model in terms of linear elastic behavior. Okay, so we have to be sure that while doing the test, the displacements are limited, that there are no free plays, and when we are going back to the zero loading conditions, the structure goes back always as well to the zero displacement. Okay, so the reference condition. Sometimes that doesn't happen because of the free plays, so it is admitted that once, twice, let's say a couple of times, we run this limit load factor test in order to check and fix possible free plays, and then we have to be sure that everything runs smooth. Okay. Once we have these results in terms of limit load factor tests, results in terms of displacement, results in terms of strain and the corresponding stress, then we have to compare these results also with the one that we can have from the numeric analysis and see if everything is compatible, if everything is the numerical model is actually predicting the right displacement and the right state of strain or stress. Then we increase the factor that we are using to increase the load from limit load factor to ultimate load factor is roughly 50%. So we multiply these loads by the factor 1.5. However, we discussed together a table, let's say an example problem table, in which we see that according to the specific type of aircraft and according to the specific direction of the loading, we can have several values of this loading factor. However, we are increasing the load factor, so we are not expecting anymore that the response of the structure is in the field of linear behavior inelastic behavior. But what we are expecting is that there will be some damages, okay, some failure around the structure. However, what we are expecting is that under the ultimate load factor test, the structure is not damaging, is not failing at all in a time frame of 30 seconds. So we have to be sure that for 30 seconds from the application of the loading, the structure is capable to survive this ultimate load factor, and then some breaks, some damages are expected, but only after 30 seconds. What is the purpose? The purpose is to check the plastic behavior, elastoplastic behavior of your structure, your test specimen, and therefore after 30 seconds we are going to see the points, the locations in which we are having plasticizations, in which we are having permanent displacement or breakings, okay? And we compare these results, the experimental findings, with the numerical ones. We are assessing the material properties because by predicting the right location of those cracks, of those permanent displacement, we are saying that the components are well designed or well analyzed from the numerical point of view, and also the material properties are well represented in your numerical model. Both tests, limit and ultimate load factor tests, are tests carried out with known loads. That is, we know very well what are these loads, and we have just to apply them. The last test that is the topic of today's discussion is the failure load test. And in this failure load test, as I already marked, loads are fully unknown. We have to find out what are these nodes. So what's happening is that in this failure load test, the ultimate loads are increased. And please note, this increase of the load is quasi-statically. Because we don't want to have any dynamic behavior included in this analysis. And we increase these loads until a part of the structure is damaged. Okay. And we would like to know these tests. So these are completely unknown, sorry, and we would like to know this. And these tests must be carried out at least once, okay, in the whole operational life or whatever design, just to see what are these failure loads and if there are some good prediction for numerical modeling, because we would like to have the information of what we call the reserve of strength. I mean, we know what is the maximum. We are not going to operate the structure at that maximum. But what is, how sure we are, how well we are going to sleep during the night, because your design, your structure is very, very, very good and does not introduce any possible damage. So this test is required at least once, okay, to identify the failure loads or estimate of the so-called reserve of strength. Okay, and that is the reason why we are doing this. Please know that generally speaking, okay, now I'm not talking specifically for this last failure test, but generally for static tests, it is recommended that the static testing is conducted on a duplicate installation in order to stress that much the installation, the test specimen that we would like to fly, for example. Okay, so we are using mockups, we are using gigs, okay, and these should be so that they are an actual replicate of the actual structure, okay, in order to have the right structural behavior tested during this kind of activities. So it is recommended that those static tests be conducted on a duplicate installation with respect to the flying one, with respect to the actual one, and that could be done, for example, using a gig or a mockup. Okay, and this must simulate the related aircraft structure. Okay, so that is the major point. Now I see that there is no screen refresh. Just one sec. Can you see the screen? No.
No, Professor.
Try to do that again. Maybe now.
Professore, vediamo lo schermo, ma non la lavagna.
Infatti sto aspettando che si... Vediamo un attimo.
Ecco, ora sì, lo vediamo.
Bene, io ho un problema. Perché un'aula invece si vede e non si vede. Vedete la lavagna?
Sì, noi da casa sì.
Ok. So I think we have to wait just 1 second that it refresh here because or you can follow using your app maybe. Okay, so it is recommended that these static tests are carried out in a duplicate installation, okay, in order to have the same structural behavior as the one that we would like to test, okay. Moreover, when referring to loads, the external loads should be discretized, okay, because we are not going to excite the loads just because we are a continuous load in the real life, okay, so that we have to discretize these loads, and therefore this is the just 1 sec, please. Okay, and this is the way that we are. I don't know what's happening. However, so talking about the external loads, this must be discretized into some LAMP laws that, and this law should be actually the replication of what is happening in real life, that is all the continuous load from the inertia, from the elastic reactions and whatever, should be moved from continuous to LAMP. So what we are having here is that the external loads are discretized into LAMP loads so that to replicate the inertia and the elastic reaction from the continuous loading. You can sit here. Now it is. Maybe you can follow. Okay, now how can we transform, how can we discretize such external loadings, external continuous loading into LAMP loads? Generally, there is a sort of, let's say, iterative process that we have to follow. Okay, so the first step is find out from your friends the continuous distribution of loads. So first step is continuous of loads. Then we assume, for example, that we can use some wing section, some specific section in your analysis, and we can use those sections to apply the external load. So we start the load discretization process by assuming some LAMP loads. Okay, so we got just an assumption. We are just figuring out the locations and the amplitude of these LAMP loads in order to replicate the effect of the continuous distribution of load that we got in point number 1. Then what we are doing as a third step is the evaluation of the elastic reaction.
Professor, there is no update in the screen.
I think that there is. Let's refresh the screen. Okay. And what we are doing now with this evaluation of the elastic reaction is to find out and to compare these the result in terms of stress and strain field to the one that we got from the continuous distribution. Okay, if we got that these two load distribution, once again, the ideal continuous loading and the actual discretized loads are giving the same stress strain field, okay. And if the components, the subcomponents are properly loaded, then we reach the goal. Then our discretization, our choice of lamp loads is okay. On the contrary, we have to go back and change positions, change amplitude in order to meet these very good correlation criteria with respect to the ideal one. So what we are is just asking those questions. Are strain, stress fields as the continuous distribution, continuous loading. Huh? Moreover, second question, are the structural components properly loaded? That is, those components, those stress are the same as we are expecting. For example, things that you know very well. Okay. So that is the kind of question that we are going to have and we have to answer after the evaluation of the elastic reaction. If the answer is yes, then we are happy, we stop the process. If the answer, on the contrary, is no, then what we got is to go back to change the load discretization process. That is, we have to change a little bit what we are doing. Can you see the whole screen or not?
No, Professor, I can see only until number 3, evaluation of the elastic reactions.
Because that is strange, because here we can see everything.
Yes, Professor, everything is fine.
So it is just you that you are not seeing the screen, I think.
No, professore,
no,
io
prof-
vedo evaluation reactions.
Same here, Professor. I couldn't see also after the third point.
I can see till stop.
Okay, so it is just
Ecco ora.
another. Because here in the class there is a perfect synchronization with what I'm writing with respect to what I'm displaying. Maybe yes, just
Now
turn
we,
the.
now we can see the screen, Professor.
Okay. Now, just to give you an idea of what is this process is, let's refer, for example, to an aircraft wing, okay? So let me take, draw a very useful picture of an aircraft. For example, like this. Okay, here you have the vertical rudder. Here you have the nose. Cockpit, okay. And then we have, for example, the wing that is going like this. Okay. Just like we have, let's say, 4-engine aircraft. Like this. And let's assume that here, for example, are two very nice specific sections Okay, because these are load ribs that are very useful to apply external loads. Bulkheads is the same. Okay. And for example, let's assume that there we are going to excite the structure. So instead of excite the whole wing with a continuous loading, for example, that is representative of the overall loading that is containing the inertia, that is containing the aerodynamic, of course, and elastic reaction force. We are applying the corresponding forces just at these two section, at this load ribs or bulkhead section. In order to do that, let's assume that I am emphasizing a little bit this. Okay, we have a dynamometer. Okay, there, and also there. That is capable to measure the actual force that is applied to your load ribs. Okay, this dynamometer is receiving a signal. Okay, so the amplitude from, let's say, an hydraulic actuator like this. Okay, and all this information concerning the actuation, that is the signal that is exciting or driving your hydraulic actuator, okay, comes from a control station. And these could be considered both hardware and software, of course. Okay. At the same time, what we are having is that we can provide the structure with a lot of transducers, for example, string. Okay, so set of strain gauge over there, accelerometers, some here, okay, like this. So all this signal is put together to form sort of information output line that goes also here, okay, to the measure. That goes once again to the control that is capable to consider all these output measurements from the transducer. Once again, we can have strain gauges, thermocouple, accelerometers, rheostat, for example, for displacement, whatever transducer that could be very useful for your testing. Okay, so once again, just to discuss some points with this drawing, what we got is that the lump loads are applied at bulkheads, load ribs, and whatever point could be used to apply external loads, and as been already defined from the iterative procedure process that we just discussed before. If there is a torque that we would like to introduce, then what we have to do is just move chordwise the applied load. Okay, so the lumped loads are chordwise shift in order to apply the right torque. Okay, and what we got to do is check if the apply loads are doing what I am expecting. Okay, so if apply loads induce the required bending moment or torque distribution. Okay, that are evaluated through the displacement strain measurements. Okay, so this procedure is done iteratively, mostly iteratively. Once we are here, there is not too much time to spend in doing that, because we already have sort of iterative procedure that has been already considered. Okay, but however, once we are doing this, we are exciting the structure where it was supposed to be and just check that everything is fine, and then we take the measurements, and then we find we test, we static test the structure considering the limit loads, ultimate and final failure. If you check the web, there are very interesting videos concerning the failure test of A380 and A350 and many other aircraft. And it takes a lot of time to do that, and mostly it takes a lot of money to do that, because we have to actually destroy the whole aircraft. So it is not a test that we can do down in the laboratory, both because we don't have such a large laboratory to host a very large structure like an aircraft, and because mainly we don't find industry that are willing to give us for free a whole structure to be broken during our tests. However, we took part to some static tests during the years, and I can assure you that are very exciting, especially when you are at the breaking point. That you can see a lot of creeping, a lot of cracking everywhere, until there is just one boom that is the signal that everything is destroyed. But you are very happy because you finally know the maximum load, so you know the reservoir strength that you got. Just to remark that we can say that this procedure, this loading procedure, this loading procedure is about 3% of accuracy. So the load optimization process, okay, is about 3% in accuracy, and that is very high. I should sometimes. And just to give you an idea, for a whole aircraft, there are not that large number of sensor and transducers and actuators are required, but they must be very precise. So for example, for a very large aircraft, we are having 1 or 2 actuators for each loading section. What we need are cables, connecting roads, drag links, that are used to transfer the information from one point to the other one. Transfer the information that is our load from the actuators to the structure. And load bulkheads are used to distribute, of course, the load over the chord, over the section. And reduce the insertion error. Okay, maybe you can see here. In addition to that, what we have also to consider proper constraint and ballast. So okay, proper constraints and ballast, okay, are used to alleviate the stress in cables. Or connecting roads. Okay. So that is what we are generally considering. And just last remark, generally what we are having is that the bulkheads are alternative okay. So that is the typical behavior, the typical process that we are having when dealing with static tests. Of course, we have to consider a lot of other matters that are the right application of the forces, the accuracy of the iterative process to find out the right lump load distribution in order to guarantee that the elastic response, the structural response, is practically the same as the one that we could have when considering the continuous load. Okay. For a full-scale aircraft, as I told you before, we have about 2 4 loading sections per wing. We have about 1 2 horizontal control wing. Okay. We have 1 for vertical control wing, some for propulsive system, and 1 for transversal load. Okay, so this is what we are having. Okay, so example. for a full scale aircraft. Okay, we have about 4 loading section. Per wing. We have about 2 loading section for horizon control wing. Horizon control wing. 1 loading section for vertical control wing. Yes, some depends on how large these are. Some loading section for propulsive system. And just 1 in case for transversal loading. Okay, just to simulate this one. Okay, now there is a question for you, and this question is about the constraint. Okay, so what do you think about the boundary condition? What do you think about constraining this aircraft or this test specimen for static tests? Okay, what do you think about? We would like to have isostatic conditions. If you are having isostatic conditions, then we are very happy because there are no issues related to the possible yieldings that the coming from the modification of the constraint reaction because we are doing something. Okay, so we are very we would like to have these isostatic conditions, but however, as you can figure out, that is not possible because structure is there, and it's not said that we could have isostatic condition when we are referring to a wing that is connected to a fuselage, for example, for our system. So we are referring to hyperstatic conditions, but there are a lot of issues because the measuring and the loading devices are modifying the loading path, and therefore what you are measuring is dependent on what is your position of the transducer. Okay, and in order to do that, in order to avoid that, maybe it is preferable to use a true constraint, so that, for example, we would like to have a portion of the whole fuselage and the whole wing that has to be tested instead of having just a wing that is connected to somehow to some dummy structure. Okay, and that's because we would like to reduce as much as possible this but influence of this boundary condition, hyperstatic condition to your measuring device. However, when referring to the full-scale aircraft, sometimes we are considering what we call the auto balance system. Okay, and these are representative of the fact that there are when the aircraft is flying, there are no boundary conditions at all because we are in a free freestyle structure. So what we are doing is that the aircraft is put on a sort of spring in the 6 degrees of freedom. So we have 6 springs representative of the 6 possible degrees of freedom. Okay, and therefore we tune these springs so that we are almost staying in the isostatic condition. So, however, we know what are the effects of the spring in some places of the structure. Okay, and that is for some comments concerning the boundary conditions. So let me write that so that you got all this information. So constraints. Okay, if they are isostatic, then there are no issues. Okay, because if you are having possible yieldings or some other effect, these do not modify the constraint reaction. Okay. Hyperstatic. And then here we are in trouble because here we got issues. Okay. Why? Why? Because we are measuring devices that are changing the load path. And if this load path is modified, then we don't know what we are measuring. So that's the reason why we would not have such a condition. Okay. In order to reduce that, sometimes it's not possible to test some other things. It is preferred to use the true constraint. Okay, that is actually mimic. The actual operative condition. Okay. For example, instead of a clamping device, for example. Okay. Plus usage is the reference that we have to consider. The alternative of that is much more better to be used is the auto balance system that are generally used for full scale aircraft testing. So for full scale testing, what we are having is the auto balance system. Okay, that is a system for which there are no external constraints. Okay, that could be very interesting if you are able to do that, because that is an actual representation of the aircraft that is flying. So not external constraint, nothing else but the aircraft. However, it is not that easy to perform. So what we are doing is, for example, the aircraft is at the parking position. Okay, and then we use 6 degrees of freedom springs, okay, or iso static constraint. For example, at the center of gravity, okay, and therefore we try to test the structure with that supporting device. We have to find out the right values of those springs, okay, but the results in terms of the elastic behavior is quite accurate. Okay, so these 6 degrees of freedom elastic constraints are introduced to provide the equilibrium. So sort of we are having the full aircraft like that, for example. That's not what I would like to do. Okay, something like that. And therefore, for example, at the CG, for example, there, what we are having is 6 of the spring that provides me the supporting of the whole aircraft, and then I apply all the things that we would like to have. Okay. Questions on this? Okay, let's have 5 minutes break, and then we keep going with the class.
Professore, scusi, una domanda.
Prego.
Non ho capito bene qual è la sequenza che dobbiamo seguire, insomma, per fare la prova statica. Cioè, non ho capito bene il fatto della corrispondenza fra i carichi concentrati e quelli continui. Qual è la variabile di controllo?
The point is that you can't have continuous load distribution, okay?
Mhm.
But what you have is just discrete loading possibilities. Okay, so the question is, where can you put these loadings, these lump loadings? What is the magnitude? Okay, you don't know that at the very first time, so you are just guessing for the very first time within your numerical model. You assume that you are having some points, some bulkheads, some sections that you can apply the load. Then you apply those loads, okay, and then you evaluate the resulting state of stress, state of strain, the elastic behavior, generally speaking, and you compare this elastic behavior, this state of stress, the strain field, for example, with the one that you got from continuous loading. If they are practically the same, then you are done. If not, you have to redo by following the chart, the block diagram that I just plotted. Okay.
Ok, ma questo stato di deformazione continuo, cioè lo otteniamo dal nostro modello numerico oppure da prove, ad esempio, non so, in gallerie del vento, che possano riprodurre il carico reale continuo?
No. The continuous loading is something that is known from your friends. No test at all. You know that. Okay. So the continuous distribution load, if you want, I can write this. Okay. Numerical or experimental, according to what you got. So that is what you got. That is your continuous loading. That is the loading that you know from previous analysis that led you to evaluation of the flight envelope, that led you from the evaluation of what could be the limit and ultimate load test factor. Okay, so you know that. The question is, how can I excite my structure with some points, only using some points instead of the possible all the continuous point that I got from the numeric analysis. So you get some positions, you get some values of the loads, and then you assess the result. What is the result? Is the corresponding elastic behavior. So what I told you, what I wrote here, is the strain stress field or the evaluation that some components or some parts are properly excited. Okay. At the very first time that it is not the case, it will be not the case. So you have to iterate sometimes, okay, in order to find out the right values of the loadings and the positions. That is numerically done, only numerically done. Then you go to real life, and this is what we got in real life. And then you start assessing that what you are having in real life is just what you got, okay, from the numerical analysis. Okay, therefore that means that within a tolerance accuracy of about 3%, okay, then you can say that you are satisfied of your loading conditions. And then once you are here, start with the limit loading factor test, ultimate, and then failure.
Ok, va bene, grazie professore.
Prego.
Professor, will you please scroll a bit up? I want to draw the picture.
Yes. Okay.
Professore, scusi,
Prego.
potrebbe ripetere perché
Perché non è possibile fare altrimenti. Questa è la risposta. If you are testing just, let's say, one bar, then you can clamp this bar somewhere and then you have an isostatic boundary condition. That's fine. If you are testing the whole wing, where are you clamping that wing? Okay, so you need more than 1 point. You need, let's say, a portion of fuselage to attach the wing to. Okay, so we are moving from isostatic to hyperstatic conditions. In order to be more closer with respect to the actual operative conditions, with respect to what you got from laboratory activities. And therefore we move from isostatic to hyperstatic in order to be closer to the reality. But however, there are issues because the hyperstatic conditions. In order to reduce such issues, we consider as much as possible the actual structural configuration, structural layout, for example, the wing and a portion of fuselage, okay, so that we are quite sure that at the connection fuselage wing, the elastic behavior is the one that we are having during real life, okay? Sometimes, and we are here having the auto balance system, we can also do a different thing. We have the whole structure, so the full scale structure that is supported by, let's say, 6 degrees of freedom spring. So we are supporting that at the CG, generally speaking. And therefore, we are just to apply different loads. The value of the springs will be so that the structure will be fully supported during these loadings. Okay. And that is the best configuration that we can have for testing, but however, that is not always feasible. So what we are having is, however, the hyperstatic conditions for large scale stuff. Okay.
sì.
Now, let's see what we can do now. Now, let's assume that we did all the tests, static tests, of course, and can we estimate, for example, the stiffness? K to me is the stiffness, okay, of your whatever system. Do you remember when you were very young, that is last year at least, static problems are characterized by this very nice problem, okay, for which we are having that the stiffness matrix, okay, times the vector of the displacement is telling you what is the force, okay. And generally speaking, if we are having the displacement field described by n components, okay, we can have an n components force vector, and the resulting stiffness matrix should be, of course, an n by n matrix. Okay, so what we can have is that the K could be evaluated by n static tests. If for which we know F, we measure, so we know the force, we measure the displacement, and then we can have the information of the unknown stiffness matrix. And for example, this could be very useful when correlating this with numerical model, or we need the stiffness from an experimental test in order to do something from your numerical analysis. Now, if we consider an independent loading conditions, okay, and these are F1, F2, Fn loading condition, then what we can do is just to recast these loading conditions in a matrix capital F, whose columns are those n loading conditions. Just to be sure, this matrix F is an n by n matrix, okay? And then rewrite the static problem, the first one, by introducing the corresponding displacement vector matrix, okay? Vector matrix because we can have this matrix of displacement that is composed by the displacement corresponding to the first loading condition. Then we have the second displacement corresponding to the second, and up until we reach the last loading condition n. And therefore what we can write is that your K matrix could be written as F times the inverse of this loading condition. Okay, so going back to the very beginning here, we would like, our task is to find out the stiffness of static test. We can consider n independent loading conditions because n is the size of your problem, n is the size of your displacement vector, for example. And therefore, just by measuring all these displacement corresponding to the n loading condition, then we can measure, we can estimate the K just by doing that matrix operation. Okay. However, please note that this could have some issues, as you can imagine, issues when evaluating the inverse of the matrix U, as always. Okay, and that is not that good. And then this procedure, okay, is very heavy in terms of number of operations, okay, due to the high number of required tests. Okay, that is n. We can do something. We can use, for example, some reduction process from the numerical analysis. Okay, by using reduction process, we can have a reduced stiffness matrix K to some degrees of freedom, okay, to R much less than n degrees of freedom, and therefore find the reduced stiffness matrix as Fr times UR, oh sorry, R to the minus 1. Okay, that is quite easier to do, but however, it is not the step, it is not the way the stiffness matrix is identified. Indeed, instead of considering this problem, the stiffness problem, we solve the problem from the other point of view, from the flexibility point of view. Okay, so we can call this method stiffness method. Now I'll show you the flexibility method. And as you can see by yourself, this method is based on the evaluation of the static elasticity from the flexibility point of view. Okay, so what we are writing now is S times F is equal to U. Okay, that is just the same problem but written in terms of flexibility matrix. And that is your flexibility matrix. Dimensions, of course, are the same, and degrees of freedom for both displacement and degrees of freedom, and the loading conditions, and the flexibility matrix is an m by n. If you would like to find out the generic displacement ui, we can rewrite this as summation, let's say from j, it goes from 1 to the number of degrees of freedom, Sij Fj. Okay. Now, from the experimental point of view, it is very easy to apply the load in just one point without any other idea to load other points than the one that we would like to have. So, for example, if we load the structure with a J load component that is equal to Dirac, delta Ej is the Dirac function, that is equal to 1 when the two subscripts are the same, on the contrary is 0. Okay, so we are just loading the structure in one point and only that point, that is the meaning of that. Then what we are saying is that the ui, the component, is just equal, or the displacement is just equal to the flexibility. And it is very nice result, because the information that you got straight from the measurement is giving you the flexibility of the whole system. Okay, of course, if you are not having any Dirac but just one point load, the result that we got is just to be divided by the amplitude of your force. Yes, just to give you an example of this approach, very easy, but just to show you the overall procedure. If we are having a system with 3 degrees of freedom, then what we got is, for example, S11 F1 plus S12 F2 plus S13 F3, that is equal to the displacement point 1, division of field 1, S21 F1 plus S22 F2 plus S23 F3 U2, and final S31 F1 plus S32 F2 plus S33 F3. So that is the static problem written in terms of the flexibility. The Sij are the flexibility entries. Okay, so for example, if you are doing, and that is the main advantage of this approach from the experimental point of view. So if your loading is so that F1 is unitary and F2 and F3 are all both 0, then what you got, S11 is equal to U1, S21 is equal to U2, U2, and S31 is U3. This is, sorry, these values from the okay, that is a quantity that you know straight from the measurements, and are giving you the information of the one column of your flexibility, flexibility matrix. On the contrary, in addition, if when F2 is unitary and then F1 equal to F3 equal to 0, then what you are having is S1, 2 equal to 1, S22 equal to U2, S32 equal to U3. And once again, you got the other columns, and those quantity are straight available from the measurements. Okay, and that is quite easy to have from the experimental point of view. Now, as a last part, maybe we can end this tomorrow. Let me show you how we can estimate the elastic property of a specific structure. And this specific structure is a slender beam structure. And this method has been developed specifically for the helicopter blades, okay, for the identification of the properties of an helicopter blade. So let me show you the reference picture, just to, for example, here, or a wing that is very, very slender, so that we can have the same result. Okay, so what you're having is the wing, or the blade, so that is the shape like this. Okay, and then we have the boundary condition, for example, something like that, that is mimicking, for example, the connection with the fuselage or the rudder hub, doesn't matter. So what we are talking about are slender structures, okay, as high aspect ratio wings or helicopter blades or something similar. Our task is, can we identify the elastic properties of such a structure? first, for such as what are the elastic properties? The elastic properties are the shear center, position in the section, and through over the stature span, the bending properties that are EI, the product of the Young modulus and the moment of inertia with respect to the axis that we would like to have for bending. We are considering for bending, okay? And please note, this is the product, okay? This is the equivalent. We are not going into details of both E and I. This is just the product, okay? And of course, the torsional properties, GJ, okay? Once again, the torsional is referring to the product of the G, the Young modulus G, and J, the factor of torsion, okay? These are the elastic property that we are going to have. In order to have this identification, what we need is the measurement of displacement, we can use a rheostat that we already discussed about, but also some optical devices, for example, catetometer.
Professore, la lavagna è bloccata da parecchio.
Da parecchio? Ok.
Sì.
Adesso riprovo a fare il restart, fammi finire questo. Plus the displacement and strain. Okay. Let me see if we can. Nothing changed? Can you see the screen?
No, non si è aggiornata.
Ma io qua vedo di sì, però.
But I can see the screen.
Ok. It seems that it works. Maybe it's your point. From your side, there are some issues.
I think
Io vedo la lavagna, ma non si sta aggiornando. Ho visto pure altri nei commenti hanno scritto così.
Ok, vabbè, allora provo. Esco. E la rifaccio.
Anche a me prima aveva dato questo problema, ma se fissate lo schermo e poi togliete il fissa schermo, si aggiorna.
Ok, sì, adesso sì.
Bene. Okay. So, what we need is some measuring device for the displacement and strain measurements, okay? Related to the displacement, you saw the potentiometer and some that are some transducer based on capacitors, but also some optical one, for example, the catetometer. The main reference, okay, drawing now could focus on such a display, such a geometry. So we are having your generical structure like this, slender structure, okay. We can assume that your reference frame is having y-axis and z-axis as usual. So y here, then the z-axis, then the x-axis, like this. We are assuming that the shear center is somewhere, I don't know, but we have to find out the place. 1 and 2, so this is the shear center position, and we are having a static loading, for example, this one. Because of this static loading, and because generally speaking, the force line is not passing through the shear center, the result of this external loading is that this structure, this slender structure, is bending and rotating because of torque. Okay. So if we enter into details of this section, what we can say is that, just focusing on the section itself, like this, for example, we have the arrow that is representative of the x-axis. Then we have the y-axis somewhere there. The z-axis. Then we are having the shear center somewhere here. To be honest, it should be also have a vertical coordinate, but not for now. We are assuming that this line on the y-axis, because the thickness is much smaller than the other dimension, is slender and beam, so we can say that at the very first side. We have the force, the vertical loading P, like this, and because of that, we are having a rotation of the structure. Let me call that theta. That depends on the distance from the clamping device. If we refer to whatever point here, we also are having displacement. Okay, that is W. That depends on the position X, Y of that. Let me introduce an additional letter, that is A, as a subscript here, A, and this A is just representing the loading condition. That is the one that we are seeing. We will see later on that there will be another loading condition. So by now, let's assume that we are loading the structure with that vertical shear P, and that corresponds to the loading condition A. So this deflection, this W, at whatever point with coordinates X and Y, because of the loading condition A, okay, could be written as the vertical displacement of the shear center, so W as C because of the loading condition A, and that of course depends on the position and the position, the actual position of the shear center in the section, plus the effect of the rotation of the section because of torque. And this, of course, depends on that rotation and the distance SCX. Okay. Please note, just and then I'm better to write the notation here, 1 and 2. Yes. Please note that these are dependencies. The one on W, whereas the multiplication of the rotational angle is in actual distance. Okay. So what is this first? Let me rewrite that. Is the deflection of a point, okay, the coordinate X, Y, because of the loading P, okay, in a sort of position A, that is our A located in A, and that is what is to me the meaning of the loading condition A. And let me write it here. Okay. Here we got the deflection of the shear center. And the last one is the rotation of the about the shear center. Okay, and this rotation times the distance of the point with respect to the shear center is telling me what is the other contribution to the overall deflection of the point C. Okay. Now, let's evaluate the rotation, the deflection of 2 points of that section when subjected to the same loading condition PA. Okay. So what we got here is that WA x y1 is equal to the deflection of the shear center x y f c x plus theta a x y1 negative y f c x. And another point, deflection because of the loading condition A, but at the point y2 is equal to the same contribution concerning the deflection of the shear center because it's still there for the given section. Theta X, but this time we have to consider a different coordinate, y coordinate. Okay. Now, if we take the difference between these two expressions, what we got is that the section rotation could be written in terms of these two displacements, WAXY and WAY2, Y1 and Y2, sorry. So what we got by taking the difference between the previous two expressions, what we got is theta A of X is equal to WA x y2 negative WA x y1 divided by y2 negative y1. And that is one first result. We are able to find out the section rotation by simply evaluating the deflections at 2 points. Okay. By the way, in order to minimize the error, these 2 points that we are using to evaluate the section rotation must be at the, for example, leading and trailing edge to reduce error. Okay. And so, for example, it could be that y2 negative 1, 1 is equal to the chord at the distance at the being span at the wingspan x. Okay. And this is the chord body. That is one point. Then what we have to say is that the rotation, the section rotation, okay, not only depends on the applied load, but also, of course, the relative position of the loading with respect to the shear center. Okay, so what we can say is that the section rotation over not only depends on the amplitude of the loading, but also on the relative position with respect to the shear center, on its relative position okay, relative position with respect to shear center. Okay, and for that we can think that a linear function, okay, links the rotation with this position of the applied load. Let me call that YA. So that what we can say is that the theta, the rotation of this section, when the load is applied at the condition A, at distance A, could be written as a linear relation like this, okay, in which M and Q are the slope and the known constant of this linear relation, okay, with respect to YA, that is the position. Okay, having said that, now if we are now considering a second loading condition, so if a second loading condition is considered, okay, it is we are applying the load at a position YB, then what we can say is that the rotation, the section rotation, because of this new condition, let me call that B, theta B, is given by the ratio of the displacement because of the loading B at the 2 points of the section Y2 and Y1, as we had before, divided by the same distance, Y1 and Y1. Okay? Now, because of time, it's better to stop here and resume tomorrow, okay, in order to see how we can find these elastic properties from such measurements. Okay, by now it is just important to memorize these geometrical conditions and loading conditions, like this one at now. Okay, questions on this? Okay, good. Time is over. See you tomorrow. Bye bye.
Professore,
Oh,
scusi, una domanda.
Prego.
Ma la lezione quella del laboratorio, quando ci sarà?
The laboratory activity will be ready once I'm ready, I think in a few days. For sure, I can say that it will be after, so next week, after Friday. By the way, this Friday, we are going to have your self-assessment, okay? And the questions will be on all the program, starting from the very first day up to tomorrow, okay? I don't know how many
Ok.
questions there will be. And Once again, it is not mandatory. It is a self-assessment, so no gradings at all. It is just for you to test your preparation, to test how is going your personal study of this subject. Okay, it is just for you. Stop just for a while and recap what we did together, and then try to answer the questions that I'm giving you.
Ok, grazie professore.
Prego. Okay. If there are no any other questions, bye bye. See you tomorrow.